Energy. We're going to start our discussion about energy with kinetic energy, or the energy of motion. The formula for kinetic energy is equal to 1/2 multiplied by the mass of the moving object multiplied by the speed of the moving object squared. And the SI unit for kinetic energy is, of course, the joule. Let's do an example where we have a mass of an object of 50 grams. It has an initial velocity of 250 meters per second. What is this object's kinetic energy in this case? So we're going to put in, what is the kinetic energy? We know the formula for kinetic energy is 1/2 mv squared. And we'll plug in the numbers. 1/2. Notice here for the mass, we want the mass in the SI unit of kilograms, so I'm going to put 0.050 kilograms multiplied by the velocity of 250 meters per second squared, and I'm left with the answer of 15.63 joules. Notice in this problem, if my mass of 50 grams is in two significant figures, then my answer should be rounded to two significant figures. So let's round that to 16 joules. Okay, now let's talk about the work-energy theorem. The work-energy theorem is that the net work acting on an object is equal to that object's change in kinetic energy. As you recall, net work on an object is equal to the net force acting on that object multiplied by the parallel displacement. And change in kinetic energy will be the final kinetic energy minus the initial kinetic energy. Or we could say that my net work is equal to the final kinetic energy, 1/2 mv final squared, minus the initial kinetic energy, 1/2 mv sub I, or the initial speed squared. Okay, let's do an example. Let's say we have some sort of vehicle that has a mass of 1,000 kilograms. It has some initial speed of 20 meters per second, and it increases its speed to 30 meters per second. What was the net work done for this to happen? Well, we know the formula for this net work is just going to be the change in kinetic energy, which is going to be 1/2 mv final squared minus 1/2 mv initial squared. So in finding net work, we're going to plug in the numbers. That's 1/2 times 1,000 multiplied by 30 squared minus 1/2 multiplied by 1,000 times 20 squared. And my net work ends up being 2.5 times 10 to the 5 joules. Okay, let's look at another example here. I have some car. It's going to move to the right of a displacement of 20 meters. It has an initial velocity of 60 kilometers per hour to the right. There's an opposing force on the car because the person in the car is applying their brakes, and so it takes 20 meters for this car to come to a stop. Okay, so what if this car now doubles its initial velocity to 120 meters per second, kilometers per hour, and so what is going to be the new displacement for this car to come to a stop? There is still an opposing force of friction, net force here, because the person is applying the brake. Now we do know that the net work done on this car is equal to the net force which is the opposing force here, multiplied by the parallel displacement. And this, of course, is we're going to call this the kinetic frictional force, which is in the opposite direction to the displacement, so we put in a negative sign. We also know that this net work value is equal to the change in kinetic energy, which is 1/2 mv final squared minus 1/2 mv initial squared. Now the car comes to a stop. So what will be the final velocity? The final velocity value here will be 0. So this whole term goes away because it becomes 0. And so when we look at this equation, I have a negative kinetic frictional force times the displacement is equal to a negative 1/2 mv initial squared. When we look at this expression, there are two variables and two constants. If we're dealing with the same car, the braking force due by what we'll call the kinetic frictional force will be constant. And the mass of the car will be constant. Of course, the coefficient of 1/2 is constant. But the two variables we have are the displacement, or the distance the car moves until it comes to a stop, and the initial velocity will change that displacement. One affects the other. So since the displacement and the initial velocity are in essence related to each other, we could say that the displacement is directly proportional to the square of the initial velocity. So in this particular problem, the initial velocity was doubled, so let's double that initial velocity. Remember that we must square everything inside, so when I square everything inside, I end up getting 4 times the total displacement, or a final d value in this problem of 80 kilometers. Oops, that would be 80 meters, not kilometers. I want to explore this problem a little bit more in terms of graphing. If we were to graph these values, and let's say we put the displacement on the y-axis and the initial velocity squared on the x-axis or the horizontal axis, what would be the slope of that line based on the above equation here? I'll put a little star by it. What would the slope be? And the way I would do this is I would rewrite this equation with the star by having d by itself on the left-hand side of the equation. So on the right-hand side of the equation, I'm left with mv sub I squared all over 2 times the kinetic frictional force. And so the constants in this problem is the mass, the number 2, and the kinetic frictional force. So what I have circled here in red in this particular graph would be the slope. Okay, the last type of energy I want to talk about in this lesson is called potential energy, and we're going to talk about 2 different types of potential energy. No matter what type of potential energy we're talking about, as long as it's potential, it will always be position dependent, or it depends on the position of the object you're talking about. Okay, so the first type of potential energy I want to talk about is gravitational potential energy, or what I will be referring to as GPE. Now, GPE has a formula of the mass of the object you're talking about, the acceleration due to gravity, g, and your height above some reference level, or your height in regards to a reference level. Now, there's also a few other things. We can also talk about an external work value, WEXT, which is equal to the mass of the object multiplied by the acceleration due to gravity, multiplied by your change in your position, or the change in your height, what I'm going to call your delta y, or your y final, minus your y initial. And we also can talk about something called by the work due to gravity. And that is equal to the same thing as your external force, but it's a negative. So negative mg y final minus y initial. If I draw you a little picture here, you'll see, let's say we have some sort of a block. And we'll draw a free body diagram on this block. It's being raised up, let's say. And so there is a force, and I'm going to call it an external force, to lift up the block. But there's also a force of gravity, or the weight, pulling down on that block. So if we wanted to know the external work done on this block, we would take our external force and multiply by the change in the height as we move it upward, and that will give me the net external. And you'll notice that my force of gravity, which is acting downward, if I wanted to know the work done by gravity, again, I'd multiply by my change in my height, and that would give me my work done to gravity. Notice because my force of gravity is acting down, that's where that negative comes in, or the work done by gravity is in the opposite direction as the work done by the external force. Okay, let's do an example. We have some sort of roller coaster ride. Here's the car to the roller coaster. It starts at position 1, and the mass of this coaster is 1,000 kilograms. And for part A, what I want you to do is find the gravitational potential energy at position 2. So what is that? What is the gravitational potential energy at position 3? Part B, what is the change in gravitational potential energy from position 2 to 3, which is also the same as the net external work, or the same as the negative work done by gravity. And lastly, C, repeat parts A and B with y equaling 0 at point 3. So let's go back to parts A and B. We're going to be making the position of 1 our reference point for parts A and B. So my y is going to equal to 0 at that position. Okay, so for part A, my gravitational potential energy at point 2 is mgy at point 2. So my gravitational potential energy at 2 is 1,000 kilograms times 9.8 multiplied my height at position 2. And my height at position 2, where is position 2? There it is. It's 10 meters above my reference level of 0. So that would be 10 meters. And so my gravitational potential energy at position 2 is 9.8 times 10 to the 4 joules. So basically mgy. Okay, now there's still a second part to part A, and that is, what is the gravitational potential energy at 3, which is going to be 1,000 times 9.8. Now position 3, notice my position 3 is below my reference point of 0, so I'm actually going to put in a negative 15. Let's go back to the beginning. Did I assign direction? Very important that we assign direction, so let's do that real quick. Let me go back up to the beginning. I do not see that I've done that, so let's do that. Let's make going up plus y, and that's how we know that I'm going to plug in a negative 15 for the gravitational potential energy at 3. Okay, so the gravitational potential energy at 3 will therefore be a negative 1.5 times 10 to the 5 joules. Okay, part B. what is the change in gravitational potential energy from 2 to 3? We're going to recall that change always means final minus initial, so that's the gravitational potential energy at position 3 minus the gravitational potential energy at position 2, which is mgy3 minus mgy2. I've already found those values, so that's just negative 1.5 times 10 to the 5 joules minus 9.8 times 10 to the 4 joules. And make sure you see those points. Okay, and so that equals a negative 2.5 times 10 to the 5 joules. And that again is my change in gravitational potential energy from points 2 to 3. Let's put a little box around that. Okay, for letter C, we're going to change our reference level down at point 3. So my gravitational potential energy at point 2, which is mgy2, which is 1,000 times 9.8. My y2 now is going to be 25 meters. And so this equals 2.5 times 10 to the 5 joules. So that's my gravitational potential energy at point 2. Let's put a little box around that. And what about my gravitational potential energy at point 3, which is mgy3? So that's 1,000 times 9.8. So what is the position at 3 if my reference level is at level 3? That value is 0, so I actually get a value of 0 joules for my gravitational potential energy at 3. Okay, so my change in gravitational potential energy from 2 to 3 will be my gravitational potential energy at 3, which is 0 joules, minus my gravitational potential energy at 2, which is 2.5 times 10 to the 5 joules. Gives me an answer of negative 2.5 times 10 to the 5 joules. That's my gravitational potential energy at points 2 to 3. And we'll put a little box around there. All right, now the second type of potential energy is elastic potential energy. That's equal to 1/2 multiplied by k multiplied by x squared. K is a constant. It's called the spring stiffness constant in newtons per meter. And x is the compression or stretch of the spring from its natural position in meters. The SI unit for elastic potential energy is the joule. Now, if I had a graph of force applied to a spring versus the stretch or compression of the string, and I got a linear relationship, I would see that the force applied to the spring, or the external force, is proportional to the stretch or compression in the spring. The slope of this line then would be a constant, so I could also say that F is equal to the slope of this line multiplied by the stretch or compression in the spring. The slope of this line is the spring constant in newtons per meter of the spring. So in essence, if I know the force that I apply to a spring, and I can find how much the spring stretches or compresses as I'm applying this force, I can graph these values, then find the spring constant of the spring, and ultimately find the elastic potential energy of the spring in joules. So lastly, I wanted to tell you that this elastic potential energy, which is equal to 1/2 kx squared, is also equal to the work done by the external force, or equal to the negative work done by the spring itself. Depends on if we're looking at who or what is pulling on the spring, that would be the external work, or if we're looking at what is the spring, what is the spring pulling on? What is the work that the spring does? That would be this one here. Okay, time for practice. Chapter 6 problems. The answers I got from the solutions manual, so these answers should be correct. Good luck. These are due Monday morning.